Hello friends, in the last video we solved a 1D transient heat conduction problem with constant temperatures at the boundaries in Cartesian coordinates using Crank-Nicholson finite difference method. In this video we are going to solve a 1D transient heat conduction problem with constant heat flux boundary conditions in Cartesian coordinates using Crank-Nicholson finite difference method. The constant temperature boundary conditions are also called Dirichlet boundary conditions. The constant heat flux boundary conditions are called Newman boundary conditions. Our objectives are to present a simple 1D transient heat conduction problem. We have Newman boundary conditions, that is constant heat flux at the ends of the bar. We discretize the domain into 5 grid spacings. We consider a single time step and solve the problem using Crank-Nicholson finite difference method. We will then vary the grid spacings and time steps and resolve the problem and obtain solutions. We have a 1 meter long copper bar. The bar is initially maintained at a temperature of 100 degrees Celsius. At time t equals 0, a heat flux FA, which is equal to 38,600 watts per meter square, is applied at the end A of the bar. At the same time, a heat flux of negative 38,600 watts per meter square is applied at end B of the bar. The negative heat flux is just an indication that the heat flux is in the opposite direction, in the negative x direction. Our general heat conduction equation in 3D Cartesian coordinates is given below, that is dou square t by dou x square plus dou square t by dou y square plus dou square t by dou z square plus g over k equals 1 over alpha dou t by dou t. Here uppercase t is the temperature and is a function of the spatial coordinates x, y, z and time, which is represented by lowercase t. Alpha is the material property called thermal diffusivity and is given in meters squared per second. Alpha equals k over rho c. K is the thermal conductivity of the material in watts per meter Kelvin. Rho is the density of the material in kilograms per meter cube. C is the specific heat capacity of the material in joules per kilogram Kelvin. G is the volumetric rate of internal heat generation given in watts per meter cube. Our assumptions regarding the material thermal conductivity is given below. The thermal conductivity along the x direction, for example Kx, remains constant. Likewise, the thermal conductivities along Ky, along the y direction, which is Ky, and along the z direction, Kz, they remain constant, and this is the homogeneous condition. Also, since we have Kx equals Ky equals Kz is equal to K, we are complying with isotropic conditions as well. For 1D transient heat conduction with no heat generation, equation 1 reduces to a simpler form. We assume temperature does not vary significantly along y and z directions when compared with x direction. Also, the heat generation term G equals 0. Accordingly, equation 1 reduces to dou square t by dou x square equals 1 over alpha times dou t over dou t, and t is a function of x and t. The equation 2 is rearranged as dou t over dou t equals alpha times dou square t by dou x square. Initial condition is given as t at x, t equals 0 is equals t in, and the boundary conditions as at x equals 0, the heat flux Fa equals 38,600 watts per meter square, and at x equals L, Fb equals negative 38,600 watts per meter square at t equals greater than or equal to 0. In this case, we are applying positive heat in both the ends of the bar. The negative value of FB is just an indication that heat flux, the direction of heat flux is in the opposite x direction. To obtain temperature, we need to solve the above PDE. We will utilize finite difference method to solve the above PDE. To do so, we need to replace the partial derivatives with finite difference approximations. We will solve the above problem using Crank-Nicholson method. Equation 3 can be represented as Tt equals alpha times Txx. Initial conditions T at x, T equals 0 equals Tn. Boundary conditions at x equals 0, Fa equals 38,600 watts per meter square. At x equals L, Fb equals minus 38,600 watts per meter square. And T is greater than or equal to 0. Crank-Nicholson proposed the following. Txx at I n plus half equals half times Txx I n plus 1 plus Txx I n. Here the second spatial derivative is he is considering it as average of the two time steps n plus 1 and n. Substituting the above into equation 4, we get Tt equals alpha times half times Txx I n plus 1 plus Txx I n. Substituting the forward time difference and centered space difference as finite difference approximations into equation 5, we get Tin plus 1 minus Tin over delta T equals half times alpha times Ti minus 1 n plus 1 minus 2 times Ti n plus 1 plus Ti plus 1 n plus 1 by delta x square plus Ti minus 1 n minus 2 times Ti n plus Ti plus 1 n over delta x square. If d equals alpha times delta t by delta x square, where d is the diffusion number, we can rearrange this equation into the form as shown in equation 6, that is minus d times Ti minus 1 n plus 1 plus 2 times 1 plus d times Ti n plus 1 minus d times Ti plus 1 n plus 1 equals d times Ti minus 1 n plus 2 times 1 minus d times Ti n plus d times Ti plus 1 n. Equation 6 is the finite difference approximation of the original partial differential equation we were trying to solve. Here I represents the node location and n the time step on the discretized domain. The finite difference stencil is given below. We have the temperature information at the bottom level, and we are going to solve the temperature information at the upper level. The above approximation is called Crank-Nicholson method. This is an implicit method, hence temperatures Ti's at present times n plus 1 need to be obtained based on Ti's at previous times n, as shown in equation 6. Equations need to be solved simultaneously as we have unknown temperatures at neighboring points for the same time step. The advantage of using implicit methods is these implicit methods are unconditionally stable. The diffusion number d as well as the time step still need to be smaller for accuracy considerations and not stability considerations in general. The truncation error of the Crank-Nicholson method is of the order of delta t square plus the order of delta x square, which is better than the BTCS and the FTCS methods we have seen before. Now let us discretize the 1D domain into nx or 5 segments or grid spacings equally spaced as shown below. Here A and B are the boundary points or the boundary nodes. Note temperatures at node 1 and node 6 are not known this time. We do know the heat flux at boundary nodes 1 and 6. We added hypothetical end nodes 0 and 7 as we are dealing with heat flux at the boundaries. According to Fourier's law of heat conduction for one dimension, Qx equals minus K times dt over dx, where Qx is the heat flux in watts per meter square, K is the thermal conductivity of the material in watts per meter Kelvin. That equation can be rearranged as dt over dx equals negative Qx over K. And this indicates the temperature gradient in kelvins per meter or degrees Celsius per meter. Let us apply the constant flux boundary conditions dt over dx at x equals a equals negative of Qx over K equals negative of Fa over K in kelvins per meter. Let us now approximate the first order space derivative using center difference approximation. We then get Ti plus 1 minus Ti minus 1 by 2 times delta x at x equals a equals negative of Fa by K. At x equals a, I equals 1. Hence T2 minus T0 by 2 times delta x equals negative of Fa by K. From this we can solve for the hypothetical temperature, the temperature at the hypothetical node T0, which is equal to T2 plus 40. Similarly, we can apply the boundary conditions at x equals b, dt over dx at x equals b is equal to negative Qx over K equals negative Fb over K. And we again approximate the first order space derivative using centered difference approximation as Ti plus 1 minus Ti minus 1 by 2 times delta x at x equals b equals negative Fb over K. At x equals b, I equals 6. Hence, T7 minus T5 by 2 times delta x equals negative Fb over K Kelvin per meter. From this, we can find out the temperature at the hypothetical node T7 as T7 equals T2 plus 40. To apply equation 6, we need to consider all the nodes from 1 to 6 because the temperatures at nodes 1 and 6 are not known this time. Let I equals 1 to 6 and n equals 0. Equation 6 is shown below. Let us substitute 2 times 1 plus d by beta and 2 times 1 minus d by gamma into the above equations. So accordingly, we get the set of equations. We'll rearrange this set of equations. At the end, our ultimate goal is to put this in a matrix form, so these set of equations can be easily solved. We'll rearrange the equations in the matrix form as shown here. The above is of the form A times Tn plus 1 equals B times Tn plus 4 times D times delta x times Tbc. Here Ti0 is the initial condition for all nodes from 1 to 6. And Tbc represents the boundary conditions. Let delta t equals 100 seconds, delta x equals L over nx equals 1 over 5 equals 0.2 meter. Then the diffusion number d equals alpha times delta t by delta x square equals 1 times 10 power minus 4 times 100 by 0.2 square equals 0.25, which is lesser than 0.5. In this case, we don't need to comply with stability criteria. We still target d lesser than 0.5 for accuracy considerations, not for stability considerations. Substituting the values for d and obtaining beta and gamma and the other factor 4 times d times delta x and fa over k and fb over k, we can arrive at the following matrix form. The above set of equations can be solved using Thomas algorithm as we did before. As the main matrix A is a tridiagonal matrix, we can also solve the above set of equations using iterative methods such as Gauss-Seidel, successive over-relaxation or SOR methods, and so on. Solving the above equations using Thomas algorithm on MATLAB produces the following results at time t equals 100 seconds. The end nodes T1 and T6, the temperatures are found to be 108.1651 degrees Celsius. At nodes T2 and T5, the temperatures are calculated to be 100.8257 degrees Celsius, and at T3 and T4, the temperatures are found to be 100.0917 degrees Celsius. Likewise, you can find the temperatures at all of these nodes at the next time step by choosing n equals 1 and so on. Graphical results are presented using MATLAB for this case. Using MATLAB or other software, you can develop codes for a general case where the number of grid spacings and time steps can be altered as desired and solutions obtained accordingly. Now we can go back to our MATLAB program. We have the thermal diffusivity alpha given as 1 e to the negative 4 meter squared per second. Thermal conductivity is given as 386 watt per meter Kelvin. The total time is given as 100 seconds. Total number of time steps is 1. And then we have the number of spatial grids as 5. The flux at NDA is 38,600. It is a positive flux going into the bar, and the flux at the other end is negative 38,600. Again, there is a positive flux going into the bar. The direction is opposite to the direction of FA. So let's run this. The initial temperature again, is 100 degrees Celsius. So let's run this program, and these are the results we got. The initial step, at the initial step, the temperatures of all the nodes are at 100 degrees Celsius. At 100 seconds, these are the temperatures. Since our heat flux is equal on both directions, we have temperature distributions which is symmetrical. Let's look at the graphical results. On the left hand side, top portion, we have the initial temperatures of all nodes, and the temperature is at 100 degrees Celsius. On the left hand side, bottom portion, at time is equal to 100 seconds, we see the temperature distribution. The temperatures at the ends are higher as the heat goes into the bar from the ends. The temperature at the center portion has the lowest value. The right hand side shows the surface plot, and there's a color scale indicating the temperature scale. Now we can go back to the program and make some changes. Let's make the total time as 2000 seconds, and the number of time steps as 200, and we'll increase the number of segments of the bar. We can change from 5 to 20, and we can rerun the program again, and we can look at the results. Here is the initial temperature of all the nodes in the bar, which is 100 degrees Celsius. This is the final condition shown at the left hand side bottom portion. The final temperature profile at when time equals 2000 seconds. The temperature varies from 116 degrees Celsius at the center to about 120 degrees Celsius at either ends. And you can see the animation of the temperature variation with time on the right hand side. Since we set the time limit as 2000 seconds, this program will run until the time hits 2000 seconds. So the temperature along the entire length of the bar keeps increasing in this case, as we are adding heat from both sides of the bar, both ends of the bar. The temperature at the ends are the highest because the heat enters into the bar from the ends. The temperature scale is shown on the right hand side. Now our program has run. We can go back to the MATLAB program, and if you like, we can change the direction of the flux. So if you are applying a negative flux, we are taking heat out from the bar. So let's see what happens. We'll run it again. In this case, the bar is initially at 100 degrees Celsius, and we are taking heat out of the bar from either ends. So the bar is coldest at the ends and is hottest at the center. So this will again run till the time is 2000 seconds. We can go back and to the PowerPoint. So to summarize, in this video we presented a 1D transient heat conduction problem with constant heat flux boundary conditions, also called Newman boundary conditions. We discretized our domain and solved the problem using Crank-Nicholson finite difference method. Note that Crank-Nicholson method is an implicit method and is unconditionally stable. Also, Crank-Nicholson method has a higher accuracy than the FTCS and BTCS methods. We varied the grid spacings and time steps and presented the results graphically using MATLAB. In future videos, we can explore more challenging problems. If you have any questions, please comment. Thanks for watching.